Hello and welcome to another video on partial differential equation. In this video, we'll be looking at its equation. In our last video, we've looked at wave equation, right? And also the introductory aspect of partial differential equation. So given this question says that solve this question given the boundary condition and the initial condition. Now, first thing first, we need to know what type of equation it is. Let's say given a question and this question is not specific, saying this is its equation. How do you identify? Recall that when we did the introductory aspect, meaning the introduction, we said for each of these equations there's a representation, meaning how you write their partial differential form. So for our wave equation, recall that for wave equation, this is how we write wave equation. The second partial derivative of u with respect to x is equals to 1 over c squared multiplying the second partial derivative of u with respect to t. This is for wave equation. Then for our its equation, we have it as the second partial derivative of u with respect to x equals to 1 over c multiplying the first partial derivative of u with respect to t. So this is the difference between wave equation and its equation. So this is the difference. So doing comparison between its equation, the general its equation, and the given question, you would see that this is under its equation. So this is how you identify, meaning if it is not stated, this is how you identify your its equation and your wave equation. Moving on, the steps remain the same. The steps in solving wave equation and its equation, they are the same. Nothing is changing, right? Now from here, recall that we said u is always a function of x and t. Do well to watch the first video on the explanation to this. We've seen why we have this as x multiplying t. So say this is equation 1. The whole concept is that from this equation 1, I want to solve this partial derivative. Then my differentials, then I substitute it. Meaning that I want to convert this partial differential equation. This is a partial differential equation. I want to convert this partial differential equation to ordinary differential equation. Me converting partial differential equation to ordinary differential equation, I then implement the techniques of ordinary differential equation. So how it works is that given from equation 1, differentiate u with respect to t, meaning the partial derivative of u with respect to t, we then have xt prime, right? This is for t function. Now for x function, the partial derivative of u with respect to x, you have s prime t. Then the second partial derivative of u with respect to x become s prime prime t. You can relate this to differentiation. In differentiation, our first derivative can be represented as x prime, where the second derivative is represented as what? S prime prime. So if this is a function and you want to differentiate this with respect to x, meaning you are going to treat t as constant. So we've differentiated x multiplying t. We want to get the second derivative of this guy, meaning same idea, differentiate this. By the time you differentiate this, you have what? X prime prime multiplying the constant. Similarly for this, that's what we did. Now substituting this answer, meaning this partial differential term, back to the general equation, meaning that the square u over the x squared, which is equals to 1 over 2 the partial derivative of u with respect to t, implies we've solved this to be this, meaning I then have s prime prime t equals to 1 over 2 multiplying t, right? Say this is equation 2. From equation 2, you will notice that I'm having the x function and the t function, meaning this equation, we only have x and t function present in it, meaning you can perform separable variable. By separable variable, equation 2 becomes s prime prime over x is equals to 1 over 2 multiplying t prime over t, say equation 3. What we've just done here is that we separate the function of x from t. By the time you separate the function of x from t, equation 2 becomes what? Equation 3. Now, the next step is to make this being an equation, meaning this x function, represent it as an equation, also represent this as an equation. So meaning from here, your absorption, or how it works, is that you say x prime prime over x is equals to 1 over 2 multiplying t prime over t is equals to a constant, right? This is equals to a constant, where this constant is equals to negative lambda square, right? Now, let's say this is equation 4. If this is equation 4 becomes x prime prime over x is equals to k, right? From equation 4, you have this. Also from equation 4, you have 1 over 2 t prime over t equals to k, say equation 6. You know, equation 4 itself, it involves both x and t function. But what you've done here is that you've separated the x function from t function, saying from equation 4, you then have equation 5 and equation 6. Now, from equation 5, cross multiply. Also from equation 6, cross multiply. By the time you cross multiply from equation 5, it becomes s prime prime equals to xk. Then taking this sk to the other side, you know, this is the left hand side and this is the right hand side. Taking sk to the left hand side, it becomes x prime prime minus x multiplying k equals to 0. Say this is equation 7. The same way you got equation 7 from equation 5, you obtain equation 8 from equation 6, meaning cross multiply. By the time you cross multiply, equation 6 becomes t prime, equating that to 2 multiplying t multiplying k. Bringing this guy to the other side, meaning you have t prime minus 2tk equals to 0, say equation 8. Now, I'm working with equation 7 and equation 8. Just like we've done for wave equation, do well to watch the first video, which is wave equation, for better understanding. I've explained all of this in the first video, which is wave equation. Now, from this equation 7, equation 7 is a differential equation. So equation 7 is a differential equation, and equation 8 is also a differential equation. The idea of a differential equation is that you want to know the function that has been differentiated, right? Now, if this is a differential equation, take note that each differential equation has their own general solution. So the general solution for this differential equation, it is different from this differential equation, right? Now, for this equation 7, just like the way we did in wave equation, the first example, this equation 7, this is the general solution. The general solution for our equation 7, meaning s prime prime minus sk equals to 0. You know, we said k is equals to negative lambda square. So let's substitute k as negative lambda square, where k is equals to negative lambda square. By the time you substitute this, it becomes x prime prime plus lambda square multiplying x equals to 0. So the general solution for this equation is given as x is equals to a cos all into brackets lambda multiplying x plus b sine all into brackets lambda multiplying x. Observe that this guy becomes my angle. I'm having cos this, meaning this is my angle. This is what we have initially. We've substituted k to be negative lambda square. By the time you substitute k to be negative lambda square, you have this. So the equation, the general solution for this differential equation, this is it. You know, from this differential equation, I want to know the function of x. This is the function of x. And this function, it is telling me that oscillation has occurred if it was wave equation we are doing. But do it to watch the first video, so you have a better understanding on all I'm saying. So this is the first equation, which is from equation 8. Now, similarly, for t prime minus 2tk equals to 0. Substitute k equals to negative lambda square. This becomes t prime plus 2 lambda square multiplying t equals to 0. So the general solution for this differential equation, meaning t is equals to c exponential negative 2 multiplying lambda square multiplying t. Observe that when this is my differential equation, this is the general solution. When this is my differential equation, this is the general solution. So we are saying that for different differential equation, they have their own general solution. They have their own general solution. Back to what we started with. We said generally x, u is always a function of what? X multiplying t. U is always a function of what? X multiplying t. And in this case, I've gotten x to be this, and I've also gotten t to be this, meaning that u, which is a function of x multiplying t, becomes substitute what you've gotten for x, meaning you have it as a cos all into brackets lambda multiplying x, right, plus b sine all into brackets lambda multiplying x multiplying c exponential negative 2 lambda square multiplying t. So this is our general wave equation. So if this is my general wave equation, I need to know the value of a, the value of b, the value of c. So this is where boundary condition comes in. From here, you apply boundary condition and you apply initial condition. You applying boundary condition and initial condition, you want to know the value of a, you want to know the value of b, and you want to know the value of c. So let's see how it works. This is our general wave equation, right? We've gotten this to be our general wave equation. Now from here, let's open this bracket, meaning that I'm multiplying this with this bracket. Me multiplying this with this, I then have u, which is a function of x and t. U being a function of x and t becomes ac, right, cos all into bracket wavelength multiplying x plus b multiplying c sine all into bracket lambda multiplying x all into bracket exponential negative lambda square multiplying t. Now to avoid constant, I'm going to assume or take note that AC is equals to D and BC is equals to E. So what we just did here is that to avoid to avoid repetition of variables, so we say AC, since this guy is a constant on its own, so we are saying AC is equals to D and BC equals to E. So let's substitute this back. I'm having U, which is a function of xt, equals to D cos all into bracket lambda multiplying x plus E sine lambda multiplying x multiplying exponential negative s square t. Now applying boundary condition, applying my boundary condition given from the question, the first boundary condition is given that u all into bracket 0 comma t is equals to 0. This is the first boundary condition, and the second boundary condition is given as u all into bracket 3 comma t is equals to 0. Now what this boundary condition means is that the interpretation to this boundary condition is that, let's say you have a material, let's say this is a vibrating material. If this is a vibrating material, this end is fixed and this end is also fixed. So say this is let's say this is D and let's say this is E. The total length of this vibrating string is x equals to 3 meter. Now at x equals to 0, D is equals to 0, right? At x equals to 3, E equals to 0. But in this case, E is not equals to 0. Now, the explanation to this is that, let's say this is a material and we said oscillation has occurred, meaning oscillation started from this very end, which is point D, towards point E. But in this case, this D is fixed, meaning no oscillation. So we are saying at x equals to 0, D is also equals to 0. At x equals to 3, E would have been equals to 0. But if E is equals to 0, it means that no oscillation has occurred at all, meaning there's no vibration at all. So we are saying that E is not equals to 0. But the boundary condition is saying that when x is 3, equate it to 0. Meaning what we are going to do in this case is that we are going to obtain what we call engine values. When we say engine values, we are saying that if from here to here is 3, meaning I'm having 1 meter, 2 meter, and lastly I'm having 3 meter. Meaning that if I can generalize a formula, I can know the vibration. With that formula, I will know the vibration when x equals to 1. I will know the vibration when x equals to 2. I will also know the vibration when x equals to 3 meter. And it is obvious that from x equals to 3 meter, the vibration will be what? 0. Right? Meaning with that formula, we then have at x equals to 3, the vibration is equals to 0, but E not equals to 0. Do well to watch the first video to see to understand what I'm saying better. Just know that from this boundary condition, what we are saying is that x equals to 0, meaning if this is your general wave equation, anywhere you see x in this general wave equation, substitute 0, then equate what you've substituted as 0 towards 0. In some cases, it might be given as u all into bracket 0, t equals to 4. Meaning once you substitute x equals to 0 into this general equation, then equate it to what? 4, right? Now, following the boundary condition given from the question, this is my first boundary condition, meaning that u as a function of x, t is equals to d multiplying cos all into bracket. Anywhere I see x, I'm substituting what? 0, because that's my first boundary condition. How do I know that I'm substituting x to be 0? Doing comparison with the general form, we said u is always a function of x and t. So in this case, I'm having 0, t, meaning x is equals to what? 0. So meaning that from here, I'm saying lambda multiplying 0 plus e sine all into bracket lambda multiplying 0 close the bracket multiplying exponential negative lambda square t. Sorry, this is 2t. I'm having 2t. Right? Now, meaning that from here, this becomes u all into bracket x, t, equating that to cos 0 is what? 1. Meaning I'm having d multiplying 1 plus e multiplying 0. Sine 0 is 0. So meaning exponential negative 2 lambda square multiplying t. Then this cancel out. I'm going to have u as a function of x, t is equals to d exponential negative 2 lambda square t equals to 0. Meaning from this boundary condition, it is telling me that when x equals to 0, and I've substituted x equals to 0 to this general wave equation, I got this, right? With what I've gotten, equate what I've gotten to 0. Why am I equating to 0? The boundary condition is telling me that this equals to 0. What if I'm having 4? Meaning I would have equated this towards 4. So that's the interpretation of our boundary condition. Now, from here, make d the subject of the formula, or it implies d equals to 0. Meaning that by the time you divide both sides by exponential negative 2 lambda square t, exponential negative 2 lambda square t, this cancel out, you have d to be what? 0. And we've said previously that the idea of boundary condition is that I want to know the constant involved. So if this is my constant, I want to know the value of d and I want to know the value of e. Since from the first boundary condition, I've gotten d to be 0, substitute the value of d you've gotten back to the general wave equation. Meaning anywhere you see d, substitute 0. your general wave equation becomes x being a function of x and t equals to 0 multiplying cos all into bracket lambda x plus e sine lambda x, right? Multiplying exponential negative 2 lambda square multiplying t. This cancel out. I'll be left with u as a function of x comma t equals to e sine all into bracket lambda x all into bracket exponential negative 2 lambda square t, right? This is my first boundary condition. After applying my first boundary condition, I end up having my general wave equation as this. Now, let's apply the second boundary condition. The second boundary condition is telling me that when x equals to 3, I should equate it towards 0, meaning I'm having u as a function of x and t equals to e sine 3 lambda exponential negative 2 lambda squared t equals to 0. But in this case, e is not equals to 0. The question is why. We've seen from this very guy, from this illustration, that if e is equals to 0, it means that no vibration has occurred, meaning this string is just straight, no vibration. No vibration has occurred, right? So do well to watch the first video when I did the introduction to partial differential equation. Now, if e is not equals to 0, the assumption is that it is an assumption, and that's how it works for general question. So the assumption is that sine 3 pi sine 3 lambda is equals to sine n pi, right? Meaning in this case, sine cancel out, make lambda the subject of the formula. Lambda becomes n pi over 3, and this is what we call the engine value. This is what we call the engine value. Now, take note that the same way we have engine value, we also have what we call engine function, meaning engine function. But how do we get our engine function? Now, we've gotten engine value to be this. The next step is that substitute your lambda. Just know that it is actually following stages, or it is following the same procedure. When we got a to be 0, we substituted a into our general wave equation that we have here, right? Now, we've also gotten, and we got a equals to 0 from the first boundary condition, right? Now, using the second boundary condition, we got lambda to be n pi over 3, meaning I'm going to substitute lambda into this my general wave equation, just like the way we did for a. Now, me substituting lambda into this general wave equation, anywhere I see lambda, I'll substitute n pi over 3. So meaning that I'm having u as a function, of x comma t, equating that to e sine all into bracket lambda becomes n pi over 3 multiplying x, right, exponential negative 2 all into bracket n pi over 3, right, all squared multiplying t. Solving this, simplifying this, I then have u as a function of t is equals to e sine all into bracket n pi x over 3 exponential all raised to the power of negative 2 n square pi square over 9 multiplying t. So this is my general wave equation. If this is my general wave equation, I need to apply my initial condition given from the question. Now, take note that this is our engine function. Right? Now, how engine function works is that you are going to write a series solution for your engine function. Now, recall that we've gotten engine value to be n pi over 3, where n is equals to 1, 2, 3, 4, 5, 6, 7, meaning integers. Back to this illustration, the total span of this material or this vibrating string is 0 to 3, meaning when x equals to 1, in this case n is equals to x. So meaning when x equals to 1, which is n, we have its own eigenvalue and is also going to have its own eigenfunction. When n equals to 2, it's going to have its own eigenvalue and is also going to have its own eigenfunction. Similarly, when n equals to 3, it's going to have its own eigenvalue, it's going to have its own eigenfunction. So if that being the case, meaning for different value of n, I'm going to have eigenfunction, right? This is what I'm saying. Now, when n equals to 1, this eigenfunction becomes u open bracket s comma t equals to e sine all into bracket pi over x over 3 exponential negative 2 pi square t over 9. This is when n equals to 1. When n equals to 2, I'm having u as a function of s comma t equals to e sine all into bracket 2 pi x over 3 exponential negative 2 square, right, pi square multiplying t over 9. When n equals to 3, I'm also having u as a function of s comma t equals to e sine all into bracket 3 pi x over 3 exponential negative 2 all into bracket 3 square pi square multiplying t all divided by 9. Then you observe that the angle in this case is following the same pattern, meaning for this first one, I'm having 1, I'm having 2, I'm having 3, right? Similarly for this exponential power, it is following a sequence order. So meaning this eigenfunction, we can have a series solution for this eigenfunction. We having a series solution, we are saying that our eigenfunction generally, we can have it as u being a function of x comma t is equals to e subscript n, right? You know, this e, it means when n equals to 1. This means when n equals to 2. This means when n equals to 3. So we are saying e subscript n. Or better still, we can use e subscript r. But let's use e subscript n, where n equals to 1, 2, 3, 4, 5, 6, 7, 8, meaning whole number, right? All into bracket 3 pi x, n pi x over 3 exponential negative 2n square pi square over 9 multiplying t. In some textbook, you see this as u open bracket s comma t equals to summation from n equals to 1 infinity e subscript n all into bracket n pi x over 3 exponential negative 2n square pi square multiplying t over 9. So this is the same thing. So it actually means the same thing. So this is our general eigenfunction. So from here, let's apply boundary condition. From this general solution, this is my general wave equation. Applying boundary condition to my general wave equation, I've gotten this as my general wave equation, right? Meaning e subscript n sine all into bracket n pi x over 3 multiplying exponential raised to the power of negative n squared multiplying pi squared multiplying t all divided by n. And the initial condition says that u all into bracket x comma 0 equals to 5 sine multiplying 4 pi x. So what this means is that when t is equals to 0, meaning this is my general wave equation, substitute t equals to 0, then equate it to this. By doing that, I'm having e subscript n sine all into bracket n pi x over 3 exponential negative 2n square pi square multiplying t over 9 is equals to 5 sine 4 pi x, right? This becomes when t equals to 0, meaning anywhere I see t, I substitute 0, just like the way we did for boundary condition. So this becomes e sine all into brackets n pi x over 3, and of course, I'm having exponential negative 2n square pi square multiplying 0 over 9 equating that to 5 sine 4 pi x, and the whole of this gives me 1. So I'm having e subscript n sine all into bracket n pi x over 3, equating that to 5 sine 4 pi x. Now doing comparison, e subscript n is equals to 5, say equation 1. If this is equation 1, also from this, I'm having sine all into bracket n pi x over 3 equals to sine all into bracket 4 pi x. Observe that sine cancel out. I'll be left with n pi x over 3 equals to 4 pi x. Cross multiply. This also cancel out, right? By the time you cross multiply, you then have n is equals to 3 times 4. Therefore, n equals to 12 and e subscript n equals to 5. Your general wave equation, which is given as e subscript n sine all into bracket n pi x over 3 exponential negative 2n squared pi squared multiplying t over 9, becomes, substituting these two values. So I'm having this 5 sine all into bracket n becomes 12, right? 12 pi t over 3 exponential negative 2 all into bracket 12 square pi square multiplying t over 9. Simplifying this, I'm having u as a function of x comma t is equals to 5 sine 4 pi t. This cancel out, I'll be left with 4 exponential negative 32 pi square t, meaning this 2 multiplying 12 square over 9, you have 32. So meaning that, given that question, this is our general wave, this is our general equation, meaning this is our general heat equation. We've modeled an heat equation for that given question. So this is how you solve similar question. It's all about we understanding the boundary condition and initial condition, then also making the absorption, saying that our constant is equals to negative lambda square, then knowing the general solution for the differential equation, then lastly substituting the boundary condition, obtaining the value of the constant, right? So this is how we go about wave equation and heat equation. If you find this video helpful, do well to give it a thumbs up and share your thoughts in the comment section. See you in our next video.